Hello again. In today's video we're carrying on with two-dimensional Newton-Raphson method, and this will be the last sort of video on root finding in the lecture series anyway. And we basically last time derived an equation in terms of vectors and Jacobian matrices for the Newton-Raphson method, and the aim today is to do an example with it where we start from a certain point and try and find the minimization of two functions. So without much ado, I'll leave you to the whiteboard. See you then. Bye. Okay, let's work through this worked example. So I'm going to start off on the board. There we go. So that's the last time we derived the 2D NR formula, which was that x vector n plus 1 equals x vector at n minus the j inverse at x of n times by big function x, and remember this big function f contains our two functions f and g. So now we're going to do an example. We're going to choose two functions. We're going to have an f of x of y equals 9 minus x to the 4 minus y to the 4, a quartic function, and g x y is x squared minus 2y plus 2, so quadratic function in x. And we want to find the points in x and y where both of these functions are 0. So we use Newton-Raphson to find the two values, because it's a 2D problem, of x and y where f equals g is 0, where they're both 0. Okay. And so we're going to start at point x0 equals what? Oops. Equals 1, 1. Sort of, you could pick it any point you wanted. We're just going to choose x0 as 1 for 1, and then we need to calculate the Jacobian. This problem, so J, remember, it's a container for your first derivatives. So you have df by dx, df by dy on the numerator on the top, and then you have dg by dx, dg by dy. And we just go through our basic calculus, and we find that it's minus 4x cubed df by dx minus 4y cubed for df by dy, 2x df by dg by dx minus 2 dg by dy. And then we're going to do the first step of the the algorithm with that in. So what we're going to do is the first step will be that x1, okay, this is shoving n as 0 into our formula, n equals 0 by the way. Your x vector 1 is x0 minus j inverse. Remember, j is not a constant, it depends on position. So we call that j of 0, x of 0, and then you've got big F of x of 0 as well. Okay. So that, looking at the components, means that x1, y1 equals x0, y0 minus, so we plug in the values of x, actually let's just plug them in actually. So x0, y0 is simply 1, 1, that's where you're starting. And then we plug in x is 1 and y is 1 into your Jacobian and take the inverse, which is just your simple formula from even A level. You get this. So this is your inverse of your Jacobian at values x is 1, y equals 1, gives you that. And then we have the values of f and g at x and 0. The value of f is 7, putting 1 x equals 1, y equals 1 into that formula, you get 9 minus 1 minus 1, you get 7. And if you get 1 and 1 into g, you get 1 minus 2 plus 2, which is 1. Okay. And this now, what we're going to do is going to use MATLAB to help us with this going forward. So I'm just going to do a hybrid of an algebra. Okay, that's the essence of it. We're navigating around in XY space using our Jacobian to find the root of two functions. Okay. Okay, so let's delete that and go to the MATLAB that I've got up in front of me. I'm just going to swap over keyboards. So here we are. Let's go to here. Okay, so this is in MATLAB. So in MATLAB, I'm going to define x0, starting point, and it's going to be 1, 1, and it's a column vector. So I transpose it. So this is a starting point. I can even put comments in here. In x and y. Okay, remember? Okay, so that's no surprise. Then I'm going to define a Jacobian at 1, 1, which is minus 4, minus 4 on the top row, 2, and minus 2. So that's plugging, that's putting x equals 1, y equals 1 in expression for j. Yeah, so minus 4, 2, minus 2. That's our matrix there. And then we're going to do the first step in MATLAB. So the first step will then be x1 is x0 minus the inverse. So we can just do that. As I said, matrix operations in MATLAB are dead simple. It's one of the great strengths of this language. So you just type in inv. And 7, 1 is the value of our big F, F and G. So 7 is the value of F at 1, 1, and G value is 1 also. And then we do that and we get this first solution, which is, so we've moved from 1, 1 to 1.6. Is the first value is 1.6 and the second value is 2.12. So that's the first step done in MATLAB. And this is going straight through so you can redo this yourself, following the lecture notes in your own time. Okay, so what we want to do now is to iterate it several times to get something close to the solution. Okay, so what I'm going to do is, following through the lecture notes, I'm on page 17 here, lecture notes. I'm going to set up some functions for Jacobian, and the g variables. So what I'm doing here is going to set up some derivatives. So df by dx as a function. So this is called, you look at your basic MATLAB thing, this is called an anonymous function. And by that I mean that you can do functions in two ways in MATLAB. You can have a separate file with your function that you want to call, or you can do it just in a single line. And this is called an anonymous function for that reason. Anonymous, I think, because it's not in a separate file. And the syntax for that is you put this at symbol and brackets around the dependent variable. Okay, and then you put your function, which is minus 4 times x cubed, in there. Okay. I think similarly we're going to do the other derivatives. df dy equals, it's just a function of that, of y minus 4 times y cubed. And then you've got dg dx equals, it's just a function of x, 2 times x. I'm actually going to suppress the output here. Like so. Just by putting a semicolon. And it turns out that dg by dy is just a constant, it's minus 2, so we don't have to have that function. Then we need to define our functions. So we define the derivatives, which will go into our Jacobian at every stage. Then we define our functions. The functions are functions of two variables. So we do the at x comma y. Yeah, two variables, 9 minus x to the 4 minus y to the 4. Okay, that's the f function. And then equally the g function is at x comma y, x squared minus 2 times y plus 2. Okay, semicolon to suppress the output. So those are your functions. So now we set that up, we can then iterate this method over several steps, starting from our initial point, and then get to the solution we seek. Okay, so I'm just going to quick check through steps now. Always good checking your starting point with these calculations, because it can save problems further down the line. So now we're going to iterate. We're going to start with x naught is 1,1 transposed again. So I really recommend you sort of try this in your own time with your MATLAB platform. Get a feel for how it works, and then we're going to iterate. So here we're iterating over 5 steps in the for loop. Then we're going to define our Jacobian. Now, because we just did one step before, that was just constants in here. Now we want to define it as a function of the state at any point. So we have df by dx is now a function of x0, the first element of x0, right? So df dx is purely a function of y, but remember y is the second element of this matrix. Okay, there's a slight double use of x and y, I guess. Here, x0 is our vector, and x01 is the x element of that, so it's just a function of x. And equally, df by dy is a function of y only, so that's the second element of our vector. You can see why we've been doing it in 2D rather than more dimensions. It's complicated enough to get the essence of the problem. And then dg by dx is just a function of x, which is the first element of x0. So, and then dg by dy is a constant throughout. So this is our Jacobian. Jacobian. Okay. And then at each step we define a new Jacobian depending on the position we're at. And then we do our Newton-Raphson method. So we're going to call the new value of x vector is the old value minus the inverse Jacobian times by this big function f, which has got f and g. So we're going to put in f, which is x. Let me just show you how it's going to be. We're going to have we'll fill in these arguments in a minute. The key point is we've got f here and g in our big function, and then we need to fill in the arguments. The arguments are the value of x, which is x0, 1, and the value of y, which is x0, 2. Equally, we have value of x0, 1 and x0, 2. Okay, let me just I'll come back with the pen in a minute. Identify these various things. So this is our 2dn Newton-Raphson, our iteration. Okay, and that's basically a big F. And I think I missed brackets off here. That's it. And then we do this thing where we swap for the next step. So what was the new value becomes the old value for the next step. X1 for next iteration. Yep. And that's it. We'll just close off the loop. I'm going to put a semicolon. I'm going to suppress the. All right, let's print it out anyway. So what we do is we do it 5 iterations here, and it's showing you x0 and x1 at each time, starting at a value of 1, 1, and we end up after 5 iterations with a value of x is 1.13. So remember this vector is 1.13. Let me just go to the pad here, see if we can just annotate this. So that's your value of x, and that's your value of y. And all we've been doing here in x and y space is we've been starting at 1, 1, and then we've been iterating just slightly further apart to root estimation. Okay, so that's your value of x and value of y, and if you just look at x0 as you go through the calculation, it iterates towards it. Okay. Let me also just try and draw a little bit on these different steps. So I might use a different color just to highlight it. We've got this thing here that corresponds to your vector f of x of n. Okay, so you're feeding a vector, which are the two components of x0, 1, 2, and that itself is a vector as well with the two values of f and g. Okay, so this is directly analogous to your Newton-Raphson method. And equally, your Jacobian now is a variant of space. So as you can see, it's quite a bit more complicated than the first order, and you need to sort of get your head around the methods. This is why I suggest you go through this yourself and make sure you understand each step that we're doing. But we can check now that is indeed the root, because as you say, as I said right at the beginning, the aim of root finding in 2D is to make sure that both f of x and f of y are 0. So we can actually just evaluate f of x and y. So if we do f of x naught 1, f of x naught 2, which is the x and y values, yeah, we've got a very small value. It's 10 to the minus 6. All right, that's good, but we also want g to be 0. And indeed it is. So the root has been found. So again, coming back to my pen, we clarify from these two values, both g of x of y and f of x of y are close to 0. So that's a good big tick on that. Now if we just go over to the board just to finish this off, if we put f of x as x, y, so in this example, if we put f of x of y, which is 9 minus x to the 4 minus y to the 4, and we set it to 0, okay, this gives us we then have, this means that we have y is now a function of x. Yeah, because we can rearrange it, i.e. y to the 4 equals 9 minus x to the 4, or y equals 9 minus x to the 4 to the quarter. Okay, so f of x and y doesn't mean a single value, it means a function. I mentioned that last time. And g of x of y equals 0 is x squared minus 2y plus 2 is 0, means 2y equals x squared plus 2, or y equals x squared on 2 plus 1. Yeah. Yeah, so one is to the power of 4 relationship with x4 in there, and the other is a quadratic. So what we have is two equations here, and when they intersect, roots are the intersection. Okay, of those two curves. And what I showed you last time was a MATLAB, and it's in the lecture notes of plotting that. Basically the idea here is I'll just do a little version of the plot that's done computationally with the in the lecture notes, but let's just complete the circle here. So the idea here is you have two curves. You have f, which is this kind of the power of 4 law with an x4 inside, so it's actually very slowly varying. That's f of x of y is 0. And then if we just do it in red here, you have g of x of y is 0. And when they both are satisfied, that's where the roots are. So the origin is here. Okay, so it turns out that the root that we came in, because we started the method at x, this is x is 1 is about here, y is 1 is about here. Because we started here, we zoned in on this root here. But there is a second root. If you started the method close to that one, it would converge onto that one. So you get 2 roots. Okay, I'm going to stop there in the interest of time. I'll see you next time. Okay, bye for now.